Okay, so let's proceed with analysis of this network. Before we proceed with the analysis of this network, let's do one. Let's simplify this circuit a bit. I mean, just like if you recall when we did our Y parameter analysis long time back, we said that we did some analysis and we found that y12 had some issues. We assumed y12 to be 0 and all, right? Because there is, what was the reason? I mean, we wanted y12 to be 0. We wanted y12 to be 0 because we didn't wanted to avoid instability, right? So, but in this case, as you can see, the y12 will not be 0 because of this capacitance CGD, right? What is y12? Y12 is a short circuit current at the input port if you excite the output port with some voltage, right? So clearly in this case, in the presence of CGD, y12 is not 0. So CGD is going to have an impact, right? So we'll deal with the impact of CGD later on. For the time being, we'll assume that CGD doesn't exist or CGD is small enough to be neglected, and we'll proceed. And in the next lecture, hopefully, right? So we'll go ahead and see the impact of CGD, right? For now, let's assume the CGD doesn't exist. So if we assume that, what does our small signal model of the common source amplifier reduce to? So this is RS. This is, let me call this RTH, R Thevenin, which is R1 parallel R2. So we have CGS, then we have CDB, we have RL, this is VGS, so this is GM times VGS, this is V0, right? Okay. So now, as usual, what should we do? We should now find out what is VGS, because now VGS is not only a resistor divider between RTH and RS, right? There is a frequency dependent element of CGS. Okay, so what will be VGS? So VGS in Laplace domain, right? If we evaluate this in Laplace domain, what will we see? We will see it's a voltage divider between the parallel combination of RTH and CGS and RS, right? So what will that reduce to? So this will become RTH by 1 plus S times RTH times CGS, right? So this is the parallel combination of RTH and CGS divided by the same thing, RTH by 1 plus S times RTH times CGS plus RS. Okay, so this means what? This is equal to RTH by plus RS plus S times CGS times RTH times RS, right? So let me express this in another format. Sorry, I missed VI, right? So this is VI of S. Also, please mind the notation. Now we switched back to capital V. Here we are switching back to capital V and small subscript, because we are in the phasor domain now, right? We are in the transform domain. These are Laplace domain or Fourier domain. We'll soon go to Fourier domain. So this, which means that in VGS of S by VI S becomes RTH by RTH plus RS times 1 by 1 plus S CGS times RTH RS by RTH plus RS. Right? So why did I choose to write in this form? I chose to write in this form because if CGS were not there, right? If CGS would have been 0, what would VGS have been? VGS would have been RTH divided by RTH plus RS, right? So if CGS would have been 0, our expression should reflect that, right? So in this expression, if you plug in CGS equal to 0, then you see that the stuff that is remaining is a scenario where we did not have a capacitance in place. So this kind of checks out, right? But what is this thing? What do you think is SCGS times that? What is that doing? So this seems like a parallel combination of RTH RS by RTH and RS, right? So that's what this is. This RTH RS by RTH plus RS. What is this? This is equivalent to parallel combination of RTH and RS. So where do you see a parallel combination of RTH and RS, and how does it come about here? So if you stare at this loop, if you stare at this input loop, right? This input side. What is the time constant associated with the capacitance CGS? The time constant associated, how will you find out the time constant? The time constant associated with this with the capacitance is, you short the input, so Vi goes to 0, right? So we had RS, we had RTH, we had CGS, and we had Vi. So we short Vi. What is the time constant associated with CGS? So tau GS is CGS times RS parallel RTH, right? So that's what is appearing here. That's what is appearing here, right? So note that we can express this term VGS over Vi also in this format, and we can also express in this format, that is RTH by RTH plus RS times 1 by 1 plus S by P1, right? What does this mean? What is P1? So here P1, or rather let me express in the more formal way, S minus P1. So what is this 1 minus S by P1 telling you? This means that there is a pole. So this implies there is a pole at frequency P1. What is a pole? Mathematically, what is a pole? Pole is the root of the denominator of the transfer function, right? So what is a pole? Pole is the root of the denominator of a transfer function, right? So in a first order, so what is the order of the system? This is clearly the first order system. I have one capacitor and one equivalent resistance. This is the first order system, right? So what is the location of the pole? Now in our case P1 is equal to minus 1 by CGS times RTH parallel RS, right? So that's what we see, right? So 1 plus S times CGS times RTH parallel RS is equal to 1 minus S by P1. So basically we replace P1 with whatever we got, and this is what we get, right? So what does this mean? what are the observations? What are the key observations here? So firstly, so P1 is a left hand side pole, right? It's a left hand plane pole. So what is meant by left half plane pole? So let me quickly refresh your basic control theory, concepts. So when we are doing Laplace transform, right? When you are evaluating anything in S domain, when you are doing a Laplace transform, what are we essentially saying? We are essentially saying that in the S plane, right? So in the S plane, this is, let's say, S plane, where S is equal to sigma plus j omega. This is sigma, this is j omega. For if we evaluate our transfer function, right? If we evaluate V0 S over Vi S, right? For all values of S. Okay, so if we evaluate V0S over VIS for all values of S, right? So, which means essentially that we are evaluating our transfer function for this entire S plane. Somewhere in this S plane, the transfer function will go to infinity, right? That's all it's saying, right? So somewhere in this S plane, right, the transfer function will go to infinity, and let's say it goes to infinity here, right? So if it goes to infinity there, we call this guy a pole. Let's say we call this P1, right? So pole is basically that location in the S plane where the transfer function goes to infinity. Now what is this telling us? Where is the location of P1? The location of P1 is, firstly, P1 is real. P1 doesn't have, in the first order system that we have, the P1 is real. It doesn't have any imaginary part. There's no j omega, which means that P1 lies on the x-axis and P1 is negative, right? So we have P1 here. Okay. And also, what does a negative P1 mean? For a stable system, P1 poles must be in the left half plane, right? So pole has to be here. So this is the mark of a stable system, right? Because if you give an impulse input to a stable system, its output should not blow up, right? So it's bounded input, bounded output stability criteria. From there, we know that the pole should be on the left half plane, right? So that is fine. So in this case, the poles are on the left half plane. That's good. Our common source amplifier is stable. That is number one. What is the second observation? We see that the pole is, so also the second observation is P is equal to minus 1 over the time constant associated with that, right? So your P1 was tau of tau gs, right? So which essentially means that for a first order system, pole is minus 1 over time constant associated with the system, right? So this is a very critical piece of information that we should keep at the back of our mind, because we will be coming back to this multiple times. You remember at the beginning of the course, we spent a lot of time finding out time constants of different types of circuits, right? Different types of first order circuits. So we leverage those learnings here. Why? Because if we know the time constant, we automatically know the poles, right? Okay, that's good, right? So that's good. So let's go back to our circuit once again. Let's see if we are given a circuit like this, right? So sorry, if we are giving a circuit like this, how should we go about finding out the transfer function without writing the KVL, KCL and everything, right? Okay, so in this case, if I have to write the transfer function, what should I do? So what is V0s by VIs? So we say that this transfer function will have two parts. One is the part where V0 where will have so let's say I call this h of s, right? Let's call this h of s. So this transfer function will have two parts. One where which will be equivalent to the case where capacitance is 0, but also note that that is equivalent to the case when s equal to 0, because where is the s term is coming from? S terms is coming from because we have a capacitance whose impedance is 1 over SCGS. Right? If S were not there, if S equal to 0 is equivalent to the case or capacitance equal to 0, right? So essentially we can express this V0 over Vi term in this form. We'll have some h of 0, right, times 1 by 1 minus S by V1. Why can we express this in this form? Because this is a first order system. A first order system will have one pole. Right? By definition, what is the order of the system? Is the number of poles is the order of the system. So first order system will have one pole. In this case, we have assumed that there is no 0, but that is not obvious. We'll come back to 0 later on, right? So if a first order system, right, doesn't have a 0, right? This is under the case of if h of s does not have a 0, right? So then we can express it in this form. Else we'll have to go back and see if this has a 0 or not, right? So we will consider the 0 later on. Let's assume that we know that this circuit doesn't have a 0, so let's go ahead. Okay, so if this is the case, what is the pole associated with the first order system? So P will be minus 1 over time constant, right? So which means that P1 will be, or mod of P1, that is the exact location of the pole, will be 1 over time constant. We know the time constant. Time constant is CGS times RTH parallel RS. We know the pole. What is h of 0? H of 0 is a transfer function when when S equal to 0, which means is a transfer function when the capacitors are open circuited, right? So the h of 0 is transfer function when C is open or at DC, right? So we know how to figure out the DC transfer function. This is simply a voltage divider. So we know what is h of 0. So we can simply write off h of 0 as RTH by RTH plus RS. Right? And we know what is the pole. We can find out the pole by inspection. So if we know the DC transfer function and we can find out the pole by inspection, and we know that, let's assume that we already know that there is no 0, then we will be able to write out the transfer function by inspection only. Okay, fine, great. So now if that is the case, so we know what is the transfer function. So now we know that h of s is some h of 0, 1 by 1 plus s by p1, or rather 1 by s plus 1 plus s by mod of p1, right, because p1 is negative. So why are we going into the Laplace domain? Because ultimately the goal is to find out, because capacitor is a frequency dependent element, we need to find out what is the effect of high frequencies, right? What is the effect of the capacitor on non-zero frequencies, right? So in other words, we are trying to find out what is h of j omega, right? So what does h of j omega mean? H of j omega means v0 j omega by v, or rather vgs j omega in this case. VGS j omega by Vi j omega, right? Okay. So what does this mean in English? This essentially means, this implies, so what is, or let me just say, so h of j omega is Vi of this Vi of j omega. So what is VGS of j omega? VGS of j omega in plain English means, this implies, this is equal to the response or the phasor response at node, phasor response across VGS when a sinusoid of frequency omega, or let's say omega, is applied at Vi. Okay. So clearly, so what is in our case, what is h of s, h of j omega rather? In our case, h of j omega is RTH by RTH plus RS times 1 by 1 plus j omega by P1, j omega by mod of P1, right? So this is a complex term, so it will have a magnitude and a phase part, right? So so this can be expressed as RTH by RTH plus RS. So, or let me simply say that what is the mod of h of j omega? Mod of h of j omega is RTH by RTH plus RS. Mod of the second term, which is 1 by under root 1 plus omega squared by mod of P1 squared. In this case, P1 is real, so it doesn't really matter you made mod or not. And what is the angle? What is the phase associated with it? The phase associated with it is minus tan inverse omega by mod of P1, right? So what does this essentially imply? This implies that if when I have the input here, let's say I have an input and I apply an input of Vp sine omega naught t, and this is where I am observing the output VGS. So what will be VGS? If input is Vp sine omega naught t and I know the transfer function is this, so what is the amplitude of the sinusoid that I am going to see at the output? So at the output I am going to see some VO sine omega naught t plus phi, right? It's a linear system. So what if I apply a frequency of omega naught? I am going to see a frequency of omega naught, right? But what will change? What might change? The amplitude of the sinusoid might change and the phase of the sinusoid might change, right? These are the two possibilities. So given that I know what is the transfer function, right? Given that we know what is the transfer function, what will be V naught and what will be phi? So clearly, by definition, that mod of h of j omega gives us what? Gives us the mod of output by input, which means I can simply scale the amplitude of the output by that mod of h of j omega. So V naught will be, in our case, V naught will be Vp. Vp is the amplitude of the input times mod of h of j omega naught, which is RTH. So Vp times RTH by Rs plus RTH times 1 by under root 1 plus omega naught squared by mod of P1 squared, right? And what will be phi? Phi will be equivalent to the phase the angle of the transfer function. So phi will be equivalent to minus tan inverse omega naught by mod of P1. Okay, okay, fine. So why is this critical? This is critical because this helps us in understanding the sinusoidal steady state output response. By the way, these are all sinusoidal steady state output response, right? This is assuming that the input is a sinusoid forever. We are not assuming that you have turned on the signal generator now and you are trying to figure out what's going to happen right from then. So this is all steady state waveforms. These are all steady state waveforms for when you have observed the sinusoid for infinite amount of time, what is going to be the response. Okay, so now so that's why the phase and the angle of mod of H is important, right? So if I plot mod of H with respect to omega, what am I going to see? So I am essentially saying that I am planning to plot this guy, right? I am planning to plot this guy with respect to omega, right? So what is going to happen at very low frequency? Let's say omega is close to 0. What am I going to see? I am going to see H of 0, right? So I am going to see RTH by RS plus RTH, right? At very high frequency, what am I going to see? Right? At omega tends to infinity, what should I see? I should see 0, right? Because denominator of the transfer function dominates. So at omega tends to infinity, it should go to 0. So somewhere between this DC value and 0, it will roll off, right? So it will do something like this. Okay, that's all good. But if I locate this value, this pole location P1 on this frequency axis. By the way, note that this is frequency in radian per second, right? This is not hertz. This is radian per second. So if we denote a frequency of P1 here, right, or mod P1 here, right? So what happens when omega naught equal to P1? As you can clearly see, when omega naught is equal to P1, the amplitude or rather transfer function magnitude goes to 1 over root 2 of that of the DC value, right? So essentially, if I mark off, right, this is 1 by root 2 of H naught. So this is H naught, right? So wherever it hits 1 over H naught will be the location of the pole, right? Okay, fine. So similarly, what's going to happen to the angle? So what's going to happen to the angle of H? What is angle of H? Angle of H is minus tan inverse omega naught over P1 mod of P1. Okay, so which means it starts off from omega equal to 0. It starts off from 0, and then as omega increases, it goes negative, right? So it goes negative. What is the value of phi at omega not equal to at P1? What is the value of phi at P1? Is tan inverse minus tan inverse of 1, that is minus pi by 4. So this is minus pi by 4. And what is the value of phi at omega equal to infinity? Minus tan inverse infinity, that is minus pi over 2. So this will go to and saturate to minus pi over 2. Okay. So you see that these type of plots have a lot of significance, because once we have these plots, we don't have to go back and write out the transfer function again. Once we have these plots, we don't have to struggle to find out what will be the amplitude and the phase of a sinusoid at any frequency. If I tell you if I ask you so tell me what is the amplitude of the output if my input is at a certain frequency 10 times P1, right? So let's say if the input frequency it is at 10 times P1, all you need to have to do is to read off this plot and find out this value. Whatever that value is, that will be the amplitude of the sinusoid of the output, right? So that is the power of this phasor plots, of this magnitude and the phase plots, right? Okay, so as it turns out, we further simplify this, right? We further simplify this and we use another approximation which we call a Bode approximation. So what is a Bode approximation? So we use a Bode approximation. What Bode approximation essentially tells us is if a transfer function h of s is of the form sum a naught by 1 plus s by p1, right? I mean, let's assume p1 is positive now because we know that it's a stable system, so there's no point in writing mod, so we'll just drop that negative sign and we'll always assume that poles are in the left half plane, right? So we'll make our notation simpler, right? So from now on we will use p1 instead of mod p1, right? Simply because we know that it's this will be, I mean, a first order system cannot have a pole on the left half plane because, I mean, system is stable, right, by default. Okay, so what is Bode approximation for a first order system? All this is saying is that if omega, which is, I mean, s equal to j omega, we know, right? If s equal to j omega, right? I mean, for sinusoidal steady state, we know that s equal to j omega. This is for sinusoidal steady state. So if omega is much less than p1, right? If omega is much less than p1, what is h of s? H of s is approximately equal to a naught, right? If omega is much greater than p1, what is approximately h of s equal to? H of s is approximately equal to a naught by s by p1, which means a naught p1 over s. So what Bode came along and said that, I mean, it will make our life really simpler if we drop this much less than much greater constraint, and we say that as long as omega is less than p1, h of s is a naught, and as long as omega is greater than p1, h of s is a naught by s plus by p1. Why? Because then you will see that we can express these smooth curves with a straight line segment, right? So essentially what Bode came along and said that, I mean, we are good in finding out solutions of straight line segments. So instead of dealing with smooth curves, well, let's say this is p1. So what we'll say is that as long as we are operating with omega, which is much less than p1, or which is less than p1, we'll consider this to be a straight line of value h of 0. And beyond p1, we'll again assume it to be a straight line but with some slope, right? The slope will be, right, a0 p1 by s, right? So essentially this is a hyperbola. So this will become something like this, right? So this is this will be something like this. Okay. Then people figured that there's no point writing, I mean, when when things become really far apart, right? When you have to deal with very numbers which are orders of magnitude apart, right? Because I mean h naught can, I mean at very high frequency of omega, right? At very high frequency, this magnitude of h can go to really small values. And if you want to then plot the same small values in the same scale with respect to what is happening at omega equal to 0, then you will not be able to show them. But there is a solution. But the solution is, if we express this in logarithmic scale, right? If we express this in logarithmic scale, then this is a linear scale that I have drawn. If we express it in logarithmic scale, then there is a hope, right? So if we express this in logarithmic scale, what will happen? So if we express as log of 20, log of mod of h of j omega, right? So this is mod of, yeah. So log 10 of this. So what will happen at very low frequency? This will be 20 log of h of 0. And what will be the other guy? So this equation is what? This equation is a naught P1 over S. The log of this is what? So log of this is 20 log a naught P1 minus 20 log omega, right? 20 log, I mean, if I'm concerned with mod, then basically this is mod, right? So it will become omega, right? Okay, fine. And if we also express this axis in log scale, by log scale, what do I mean? What I essentially mean is that if, let's say, this is 1 Hz and I go some increment and I say this is 10 Hz, right? Then if I go equal increment again to the right, this becomes 100 Hz. If I go another same equal increment to the right, it becomes 1 kilohertz, and so on, right? So equal increments on the x-axis multiplies the frequency. That's what log scale essentially implies. If x-axis is log scale, which means x-axis is also increasing exponentially, right? And y-axis is also in log scale, right? This is also in log scale. Then this becomes a log plot, right? So for every 10x increase in omega, how much does this guy reduce? For every 10x increase in omega, this guy reduces by 20 dB, right? So by factor of 20, which is often referred to as dB, right? So there is another popular way of referring this. Instead of doing this, we keep the P1 and S together, so we call this. So essentially, then this becomes this, right? So at omega tends to infinity, where will this red line go to? The red line will go to minus infinity dB, right? So this is now in dB. The units are in dB. Okay. So in the top plot, if omega tends to infinity, mod of h will go to 0. But because we are doing a log plot, at omega tends to infinity, this will go to minus infinity, right? So essentially, what is the moral of the story? The moral of the story is that if we do a Bode approximation and we further use that Bode approximation to plot everything in a log scale, right? So we can replace these smooth curves with straight line segments. So moment we can replace them with straight line segments, things become easy, right? So because this breakpoint here, what is this breakpoint? This breakpoint will become the pole. And what is a pole for a first order system? The pole for a first order system is 1 over tau, right? So you see that, I mean, everything is clicking, right? So at the beginning of the course, we found out how to figure out a pole. At the beginning of the course and throughout the course, we have been dealing with DC transfer function because we have been neglecting capacitor, right? So now if you have to put 2 and 2 together, if I have a frequency dependent component, at least a first order frequency dependent component, a first order low pass frequency dependent component, first order low pass frequency dependent response, then I should be able to look at the circuit and predict its output, right? What will be the output? The output will be the gain at DC will be the Bode approximation is telling us the Bode plot will be flat till we hit the first pole. What will be the flatness? What will be the value of the flat portion? The value of the flat portion will be the DC gain. Then you hit the first pole. What is the location of the first pole? The location of the first pole is at 1 over time constant. And then what is happening after the location of the first pole? It rolls off at minus 20 dB per decade, right? This is minus 20 dB per decade. Okay, right? And another reason Bode approximation is immensely useful is because now we don't have to deal with the entire transfer function. We can deal with piecewise line segments of the transfer function. Okay, since we can deal with the piecewise line segments of transfer function, we will be able to make our life a lot easier. We don't have to use higher order equations, right? So the whole part, the whole thing that we are doing in circuit design is to make the analysis simpler so that we can make quick and easy decisions. And we can make quick and easy decisions if the analysis is simpler, right? And we know how to deal with first order circuits. So we are trying to break everything down into system of first order circuits. That's all we are doing, right? So let's stop here. In the next lecture, we'll see, when we put the entire common source amplifier together, what will be the eventual frequency response. Okay.